Okay, so thanks very much for giving me this time to present this work. So feel free to interrupt me. I mean, I haven't prepared anything very formal. I understand it's not super formal, so please interrupt me with whatever you want. So what I'm going to talk today is some recent work that we have been doing, and it's basically reflected in two papers. One that I led and that is now accepted, and it's also posted in the archive. And the second one, which is submitted, not posted yet, but soon, led by a student of Avishai Dekel. And both are related in the sense if we try to use somehow machine learning to study the properties or to revisit a problem which is, or an astrophysical problem, which is the physics or properties of clumps in galaxies using CANDELS data. And so I thought that could be a thing to present in this group because it uses CANDELS data, and I do machine learning, but there's also a bit of SED fitting. So you might be interested in this. Anyway, so just as an introduction, a quick introduction for those who are not very familiar with the idea, the topic. But I think we know for now several years that the morphologies of high redshift galaxies, I mean, between redshift 1 and 3 in CANDELS, specifically when you look them more in the UV res frame, but also in the optical res frame, present this kind of clumpy structure, which is that we see some star-forming disks, but also, as you can see in these images by Yi Cheng's papers, you see that there are some clumps there, quite bright, as I said, mostly in the UV. And if you quantify how many of those present clumps, it depends again on the fraction on the mass beam you look at and redshift, but you can go up to 60% at redshift 1-ish of galaxies which present this clumpy structure. So there's also, since we know these, there's been this debate of what are these clumps? Is this an artifact from resolution and we see these blended objects, or really giant clumps that start forming? So understanding the nature of these clumps and what is the impact in the in subsequent evolution of morphological evolution of these galaxies is something that is still open debate. So in particular, there are several questions. I'm going very briefly on these. There's a lot of literature on the topic, but there are several issues. For example, so what's the origin of these clumps? Are they formed in situ within the galaxy because high redshift galaxies have more gas and also more turbulence, so this creates a condition in the ISM to create these massive clumps. And there are simulations showing these, that you can indeed in unstable disk create this gravitational collapse and create these clumps of star formation. The other option could be that these guys are in fact a reflection of enhanced minor merging at high redshift, and in fact they are formed ex situ in other galaxies, and they're just small clumps of stars or small galaxies falling into the galaxies. And both scenarios have been put forward. Now, if you want to distinguish between these scenarios, one way of doing it at clamp stellar mass functions or the stellar masses, because they will predict, these scenarios will predict different distributions of clamp mass. For example, if you form clamps in situ, the shape of the clamp stellar mass function is very particular. It follows a slope of close to -2 and has a particular shape, which is not the case if you are accreting these objects. So this will be one of the things that I want to discuss today. The other thing that's interesting and is already discussed in the literature is how long do these clamps live in the galaxies? And again, now there are different scenarios. Some models predict that these clamps will be able to, are dense enough to survive disruption, and they actually can be formed in the outskirts of the disk, and then through dynamical friction migrate towards the center and even contribute to the build-up of the bulges we see today. And this will be a scenario what we call a long-lived clamp, in which is able to survive the disruption. While there are other models that said that they are not enough gravitationally bound, so feedback among others can destroy these clumps, and they won't survive enough to migrate towards the center. And just what we see is, very short-lived clumps that are there for a moment, but then will be disrupted and don't contribute much to the buildup of the stellar mass of the galaxy. And again, both scenarios are present in the literature. And what's interesting about these is, in addition to understanding the physics of clumps, is that you can eventually put some constraints on feedback, because models have shown that if feedback is too strong, you will destroy the clumps. All clumps will be short-lived. Whereas if the feedback is not, it's less strong, then you will have more long-lived clumps. So by looking at this in the observations, you can indirectly also put some constraints on how feedback works in these galaxies. Now, if you want to put constraints on lifetime, this is even more complex. So, for the origin, you can use stellar masses, as I will show later. For these, you need to go and estimate ages of the stellar populations of these clumps. And this is, estimating ages of galaxies is already complicated. Now, if you go to clumps with HST resolution, it's way more complicated. But then I will also discuss in the second half some ideas we had on machine learning on how to estimate these indirectly.
Mark?
Okay, yes, go ahead.
I just had a question. I'm not trying to be picky, but the way you drew the long-lived clump migrating, it migrated along a spiral arm.
Right, yeah.
Do we expect that to really happen? Do we have any idea how they should migrate?
No. In fact, this is just a cartoon. You're right. So, no. In fact, in most of the cases, these in the images I showed you, the disk at high redshift don't present clean spiral arms like that, right? So they migrate towards the disk through dynamical friction. So we expect them, I think, to be spiraling a bit, but not across the spiral arm, I would say.
Thank you.
Okay, so more questions. So we decided to try to address these two questions, and it's not that it's the first time they are addressed, but we try to do these from an original perspective. On the one side, combining both observations and simulations, on top of a layer and on top of these a layer of ML. So the observations, we use CANDELS data, so no need to introduce those. For the simulations, we are using the zoom-in hydro simulations by the Deckel group, which probably you know about it, but this is a zoom of 35 or 40 galaxies simulated in a cosmological context, but we simulate only these halos. And the reason we use these simulations instead of a full box hydrocosmological simulation is that in order to resolve clumps, you need to have a very high spatial resolution, and you don't get these with, let's say, Illustris or TNG simulations. But you get this in a zoom in. So the price to pay is that you have, of course, a small sample, but for our purpose, it was enough. And what we did also with these simulations, we don't only use the output of this simulation, but we run them through radiative transfer codes to generate mock HST imaging or CANDELS data as if observed with these simulations. So basically, we run a radiative transfer code. We also make some assumptions about dust and create these mock images in different filters to which we add PSF effects and noise to mimic at most the CANDELS data. But with the advantage here is that we know where the clumps are and the physics of the clumps of these particular galaxies. Okay, so we start with these, and so we try to go step by step. And the first what we need to do in order to analyze the clump properties is to detect the clumps in galaxy images. And this is again a problem of image analysis, essentially. So it's not, again, the first time people do that, and then there are many ways of doing it. The standard way or automatic approach, I think, are all variants of this algorithm by Yicheng. In essentially, since clumps are high, frequency blobs on a smoother, profile, you can, do these with a kind of high pass filtering by, smoothing and then subtracting, and you get the high frequency peaks, and then you detect these guys. This is, let's say, the standard approach. Now, this requires a little bit of manual fine-tuning, and also is pretty slow. So Yicheng run these on a couple of CANDELS fields and in only 2 or 3 wavelengths. So we wanted to see if, given that this is, a filtering, you should be able to mimic these with convolutional neural networks, which at the end, what they do is exactly filtering, but without putting a priori any filtering, or just letting the network find what are the best filters to use. And so, well, this is the first thing that for which we use machine learning is to detect the clumps. So essentially, we built a state-of-the-art neural network for these, which we call segmentation neural networks. These are UNet-like, and the idea here is just that we put as input an image stamp with a galaxy on it, and we ask the network to predict a binary mask where the positions of where the clumps are in this galaxy. So it's pretty straightforward in that respect. So since we need to train, this is a supervised approach, you need to train this network. What we did again here is a very simple approach, a very simplistic, I would say, in which we take just a search-seek profile for the galaxy, and we put on top of these some unresolved sources that are our model for clumps. You don't see them here, but they are here. This is because we know where we put them. So we keep also a binary mask where the clumps are. So you see these are faint clumps that are hidden by the profile of the galaxy or the emission of the galaxy. And so what the game here is to ask the network, okay, I give you these, I know where the clumps are, find a way, to make this mapping, okay? Again, this is a very simple approach because galaxies are by definition symmetric in this here, and also are made with search-seek profiles. But this is what we started with, and see how well it generalizes. We made also other tests, but I will skip them for now. So if you do this and you plug this into this network, it works pretty well. Just an example of how we run these on 7 bands. Here I'm only showing 5, but and you see that these are completeness essentially as a function of the luminosity or the luminosity ratio of the clump or the contrast of the clump. So higher contrast is around here, faint clumps. Faint clumps are here, bright clumps are over here. And you see that, so these are solid lines are completeness, so you're close to 100% when the clumps are bright enough. And this is purity, you are close to 90%, which, I mean, for this simple analytic profiles is expected, but indeed, so there's no a priori modeling of the filters, we let the network find it. You see that in the infrared is a bit lower, and this is because of resolution.
Mark?
Yes.
So in this, how's the purity estimated? Like, is it by comparing it to the ground truth masks?
Exactly, yeah. In this particular case, this is on simulation, so you know the ground truth.
Right.
So the question is, so this is a comparison now with Yi Cheng's algorithm, and this is now this is now applying this model to real CANDELS galaxies, so without any transfer learning, in which we put some mock clumps. So we know where the clumps are, but we apply instead of search-seek profiles to real CANDELS data. And again, what I'm showing here is the completeness as a function of clump contrast. And you see that, our algorithm is more sensitive at low luminosity, especially than the previous method by Yi Cheng, which is also encouraging and also telling us that, it generalizes quite well to these real data. Okay, so with these tests, I'm going to, so first thing is to detect the clumps, and now I'm trying to go over the results of the different papers. And the first thing I wanted to address, I told you at the beginning, is what's the origin of this? What kind of constraints can we put on the origin of clumps if they are formed in situ or ex situ? And so first thing we want to do is, so I said, it extrapolates kind of okay when you go to CANDELS data, but this was again simulations. So the problem is in the observations you don't have any ground truth, so the only thing that we can do is compare with previous measurements and see that we are consistent. What I'm showing here is just a consistency test, and we compare the luminosity function of the clumps, so how many clumps we have per beam of luminosity. So what we get with our data, with our model, which is the blue lines over here, in the UV rest frame, and in the optical rest frame, which is red, and as compared to the measurements by Yi Cheng with his method. And you see that globally at the bright end, we agree kind of, it's more or less consistent, giving the case that, the methods are completely different, and that we train on simulation. So it's quite okay. And you see that, so these solid lines are the completeness corrected measurements by Yi Cheng, and you see that we follow these better than the uncompleteness. So it confirms that we are a bit more sensitive. anyway, this is just to show that we can extrapolate these. I can give you more details about these, but it extrapolates rather well to real data, even though it's trained with simplistic simulations. Okay, so once you get these detection of clumps, and I think so, what we wanted to do to check about, to put constraints on the origin of those is we need to get stellar masses. And here I don't use any fancy thing. We just use CD fitting. So we measure the, the luminosity of the clump in all the bands. So 7 bands. We are using here the Goods fields, and we run a simple tau model. I know this is not, nothing very sophisticated, and probably the star formation history of clumps don't follow a tau model. We tried different star formation histories, but it didn't make a difference. But it is something that maybe it's interesting to discuss with you guys about. Possible follow-up is to use, non-parametric star formation histories to see if we improve things because of what I'm going to discuss later on. Anyway, so we use bagpipes to do these, and so what we see is, for our purposes here, at least, so the uncertainties or the posteriors on the stellar mass are rather constrained. I mean, are kind of okay with 0.2 more or less deck in uncertainty, or 0.3, which is, I mean, I don't expect to get better than that. However, ages, of course, are completely degenerate, and that's why that's something that we'll discuss later on how to improve on these. So these are then, once we get the masses, this is an example of clumps. Again, we do the detection in several rest frame filters, so both optical and UV. And so these are some clumps that are detected in the optical rest frame. And you see that in the optical rest frame, for example, in these objects here, I don't see you see my cursor, but the clump is barely visible, and you see it clearly in the UV, but the network is able to detect it here in the optical. So you see that there are clumps that are not highlighted here. Is because I'm highlighting only the very massive ones in this particular figure, but they are detected anyway. Okay, so let's go over one of the first results. So the idea we have here is try to put constraints on the C2 origin of the clumps. And one way to do it, as I said you, is looking at the clump stellar mass function, which essentially counts the number of clumps as a function of the clump stellar mass. And what I'm showing here is what you get from the simulations, from the Villa simulations. So in 3D, you can go and measure, detect the clumps based on the gas and so on, and measure the stellar masses of them. So this is only purely simulated, no observational effects. And you get this kind of shape for the clumps predicted by the Villa simulation, in which you have a slope here which is close to -2, and this is what you expect from an in situ origin of clumps. So you see the stars here are in situ formed clumps. Ex situ clumps, however, don't follow this slope and tend to be, well, indeed, in this particular simulation, much less frequent and also more massive, right? So you see by looking at this kind of plot, you can put constraints on how clumps have been formed by looking at the stellar masses and the stellar mass distribution. Now, if you then say, okay, let's compare these two observations. So now I can compute from the sample, the CANDEL sample, by using this machine learning detection technique plus the CD fitting, I can compute the stellar mass function of clumps in CANDELS. And this is what you get, right? So again, I'm showing here the predicted or the predictions from the simulation, and this is what you measure in CANDELS. So you see it's a huge difference. First, the peak is around 10.8, almost 10.9 solar masses in clumps. So you see a decrease here, but it's probably due to incompleteness. But in any case, you see a way more massive clumps than you will predict in the simulations. And this is something that is kind of well known somehow, in the sense that the masses we measure for these clumps are very high when you use HST images. And in fact, in the few examples we have with gravitational lensing estimates, we know that these stellar masses are, I mean, people measure lower masses. So there's a kind of debate about, are these real very massive clumps, or, I mean, it's just that we cannot measure masses here. So if you just do this and stop here the comparison, you would say, okay, match. So what we measure in the observation is completely different. Now you might wonder, is this then observational effects? So what you can do is then, okay, now what I told you about, we take the simulation and we mock observations and we create mock HST imaging. And now we run our pipeline exactly as we did in CANDELS, but on the Vela candelized data, we call it, right? And this is what you get, okay? So you see you get much closer now. So from these green here, just by introducing observational effects, this is the mass function you get. Okay, so you see, so the observational effects are completely dominating your estimation of the masses, and it's very hard, given these, to put any constraint on what's the actual, intrinsic slope of the clump stellar mass function and the masses of the clumps you're measuring. What this is telling you is that the simulation might be compatible with the observation, at least in terms of, if you add up the observational effects, and you see that, you can somehow you cannot directly rule out this in situ origin of the clumps based on this measurement, just because there's something going on in the measurement. So what's going on? And so what we did then is try to investigate what's happening here. Yes.
Sorry, if you can go back. Yeah, just wondering, do you know what main observational effect is causing the stellar masses to be overestimated?
Yeah, I'm trying to describe. I don't know exactly an answer. I don't have an answer exactly but I can give you some hints in the following slides.
I'll be patient about that. Then the other question is, in theory, you could have several different models like Vela that had different slopes and candelize all of them and see if the CANDELS observations rule some out.
Right. Yes. No, exactly. So the problem is that, as I said at the beginning, you don't have many zoom-in simulations with the resolution of Vela. You could use FIRE, that would be one. But indeed, this is a good point, yes. And then you can use this, what the plan now, for example, in Vela, what they do in Vela is that they run the same exact initial condition by changing the feedback strength. So you can eventually, run all this pipeline again and see if you increase feedback, if you get closer or farther from observations, and eventually put some constraints on that. Anyway, so to go on with what, to answer the first question, what is causing these? So what we did is, since in the simulation, you have all the information, so you know what is the stellar mass of the clump, let's say the true stellar mass of the clump that you get from the 3D metadata of the simulation. And so you can go and say clump by clump, saying, okay, what's the stellar mass of the clump I got in 3D and compare to the stellar mass you get from 2D SED fitting. And what you get here is that there is a correlation, although with lots of scatter, but this is the median. But indeed, what you see is that there's huge overestimation, which can go to a factor of 10. So when you get the stellar mass of the clump and you go through this pipeline and try to estimate it from HST imaging and SED fitting, you get a factor of 10 overestimate. Now, which then creates partly this effect. So what is causing these? I don't have an exact answer, but I'm showing here some hint. For example, the color code here is the distance of the clump to the galaxy center. So redder is farther away, and blue is closer. And you see that this kind of trend in the sense that close clamps or clamps which are close to the center are more overestimated. And so this points, for example, to a problem of, when you measure the flux of the clamp, you might be, because of limited resolution in the HST imaging, you might, get some contamination from the background of the emission of the galaxy. Even if you subtract it, you get some contamination, which creates this overestimation of the mass, for example. There are other effects, like, as I said, you have blending of clamps. So you can have, because of the resolution, you are measuring, when you detect a clamp is in fact a mixture of different clamps. And this also contributes to the effect. We check that. And also, I told you at the beginning, I'm using a very simple star formation history. So this can also be, biasing the results I get on the clamps, because clamps clearly don't follow a tau model. But all these effects get together, and at the end, what you get is this overestimation. So, yeah. So what we want to, yes.
Sorry for interrupting.
No, go ahead.
Have you like one of the things that you mentioned is that the possible overestimation of flux based on where the clump is in the galaxy. Have you like for the CANDELS galaxies, you at least have some estimate of what the Sersic indexes or structural parameters are? Have you maybe tried to correct for that effect in a way in subtracting based on the distance of the clump to the center of the object?
Yeah, so when we do for the flux, we try to subtract the profile of the galaxy using the Searsic profiles. Yes, so this is already taking into account these, but I think this is on top of this. Yeah,
so even though if you subtract it, you are still seeing like on an order of.
Yes. And we are not the first of in finding these. So other people are quoted that other people that not systematically as we did here, but on selected cases on simulations, we see this effect of our estimation. So instead of, I mean, what we wanted to see, okay, these are, we didn't investigate exactly what is the effect causing these. We see it's a combination of effects. So we try to do instead is using again machine learning. So by the way, this highlights, I think, one of the conclusions of this talk would be that HST imaging has lots of limitation when you really study, you really start hitting the limits when you start to study and want to study resolve properties of distant galaxies. And this is clearly highlighting these, how, you know, the observational effects can be severe when you start really going into the details of galaxy structure. And fingers crossed, James Webb will be really helpful here. But in any case, so I try to do this is, can we push forward these and kind to, you know, recover somehow the information? And we went and used again another layer of machine learning here. And the idea was, okay, we know there's a correlation here, which is based and this is purely observational effects because, I mean, it's simulation versus simulation. So can we, you know, train a model to reduce or, you know, correct for these effects somehow? And when we trade here, you know, somehow a probabilistic neural network in which we gave as input the bias stellar mass plus some other secondary parameters that will, you know, contribute to this bias. For example, the distance of the clump to the central, so center of the galaxy, and try to get a corrected stellar mass, which in our case will be, you know, the 3D based estimate. What we get here, it is a probabilistic network in the sense that we get not a value here, but a posterior of what would be the corrected mass based on this input and the prior knowledge we have from Villa. Now, if you go and do this is what you get, and you see that it becomes much better. So you are able somehow to, this is exactly the same sample I was showing before, and you see, as compared to this biased estimate, you don't only, you know, practically, you know, eliminate the bias, but you can also reduce a little bit the scatter. And so basically, by using this second or layer of ML, you are able, you know, to recover somehow the true mass or the intrinsic mass of the clump, even though it was overestimated with the pure SED fitting, and we don't know exactly what are the different effects, but you try to, in a nonlinear way, take them into account and correct for that.
Mark?
Yes.
So this is really cool. And so when you do this sort of second order correction, were you able to figure out like which of the input features was the most important for like figuring out the correct mass?
That's a good point. We didn't, because in fact, what we use, I use a neural network, and I could have used another technique, but since I wanted to get a posterior, I used a neural network. And the point is that after a few layers, you don't know exactly which one is more important. So this is something that, you know, it's hidden there. I don't know which one is more important. I made some tests, you know, removing indirect tests by removing some parameters. And I would say that the most important for sure is the 2D estimate. If you miss the estimate from SED fitting, it's impossible, which makes sense. But the other parameters contribute marginally, but they contribute a little bit. The distance, for example, this is what I'm showing, the distance is important.
And is it possible? So I don't know if in this, like into the neural network, do you also feed the clump SEDs?
No, I feed only the clump mass from the SED. So like this is a very simple correction. I just run the SED fitting, I get an estimate of the mass, I know it's biased, and I say, okay, this is the mass you get, this is the mass you should get based on the simulation, so find the mapping. Right.
Would it make sense to like directly give the SED? Do you think that contains more information?
Yes, but this could, indeed. But yes, this I agree with. Yeah, this follows, you know, a kind of historical way of doing it. So we started with SED fitting. We said, wow, it doesn't work, and then can we correct that? But now, you know, it's true that we could just go and do the full SED fitting with ML. But this will be, you know, I think biases that can introduce. Here, at least, I know what's the estimate from SED fitting and just apply this correction.
Right, makes sense. Thank you.
So once you do that, you can go and say, okay, let's correct the stellar mass function. And then you apply, now you compute the stellar mass function of the clump. So remember, this should be compared to these, in which we got these very different shapes and very high masses. We apply the correction, and as expected, the mass function now, it looks completely different, and it matches. So this red, again, is the Vela candelized, and blue is candles. So they are a bit on top, a bit more, more clumps at a given mass, but you match much better, the intrinsic 3D clump stellar mass function. You see that at low masses here, we start to deviate, and this is because completeness. So we are not complete anymore below these stellar masses, but in the range in which we are complete, it works more or less okay. So it means that despite all these observational biases, we are able to somehow to recover this clump stellar mass function. And in fact, by doing this, you see that the candles observations really, despite of some differences, point out towards for the majority of the clumps an in situ origin. Otherwise, you want, at least in the simulations, you cannot form this amount of clumps by ex situ. They are all formed in situ here. So the in situ are over here. So the fact that you get this shape, first shape, and also masses of the clumps once you correct, points towards majority of in situ origin for these clumps. But also important, we revisit, we put a different limit on the masses of those clumps, and this in fact is in better agreement with gravitational lensing, right? I told you at the beginning that the few measurements that exist with lens data, and which you have high resolution measured, clump masses around 10 to the 8 or 10 to the 7, and this is in fact what when we correct, we are more in agreement with these, which alleviates this tension between the different techniques. Now, everything I'm showing here is just for a small sample in candles, which have the same properties of Vela, right? Because you want to compare, again, I told Vela is a zoom in, so it has only a few halos. So when we did this exercise, to compare apples to apples, I will select, samples of candles that follow the same Vela distribution in terms of stellar mass and redshift. Now you can do, once you know this correction, you can extrapolate. But again, this is an extrapolation and say, okay, I trust my correction for this Vela candelized, and I apply it to the all candles data set. This is a bit risky, again, because this is extrapolation of ML. And so you need to take this with a grain of salt, but you can do this exercise. And if you do that, this is the stellar mass function you get for candles, for clumps, and you see more or less the same behavior. So I pick up to the 10 to the 7, and it decreases because of completeness, this slope over here, and then, so most of the clumps are below 10 to the 9, and then you see this huge mess here. So for massive clumps, you have lots of uncertainty. So I skip what are the two, so the two colors here are two different corrections, and with different priors that we use in our machine learning model. So you see that because of the priors, it can change a lot the constraints in the high mass end. And this is because since Vela galaxies don't have very massive clumps, when you try to correct them, it's very uncertain what are the actual numbers above a given mass, right? But you see that this is well constrained, and here we measure this uncertainty. So we cannot say how many of those are here, but we can put some constraints on. But I think one of the safe results is that the majority of the clumps are not as massive as we observe here when you don't do any correction. And again, as I told you, this is in better agreement with lensing, in which, for example, in this example, they measure masses of the clumps, which are around 10 to the 7, 10 to the 8, but not, a peaking over here. Then, so poor constraints in here, I just told you. Okay, so I don't know how much time I have left. I'm going to go quickly on the second paper, which is also, I put some, I told you about some constraints on the in situ, ex situ origin. I'm going to talk about constraints on lifetime. Remember, so you can have long-lived clumps, short-lived clumps, and this is a bit more tricky because you need to estimate ages in principle. So we called again ML to the rescue here, and we had this crazy idea of saying, okay, we cannot get ages from SED fitting. I mean, if masses are so biased, forget about ages. But what about, just classifying, turning this into a classification problem? And again, using as a ground truth the simulation. So what we did now is we take this mock imaging from Villa and say, okay, let's detect clumps there when we know these are true 3D clumps. And since it's in the simulation, for every clump, if it's long-lived or short-lived. You can go back in time and see for how long what is the age of this clump, and classify them with a given age threshold. You can say these are long-lived or short-lived. And so what we do is we take small stamps around the clump, only the clump, in 7 filters, so it contains the colors, and we feed these to a CNN and ask for a very simple classification problem, which is this clump I'm showing you, is this long-lived or short-lived? And again, this is based on the definition of the simulation. And so we transform this regression problem of getting the age, which is extremely complicated, into a classification problem, which at the end is putting clumps in boxes, but it's putting a hard limit instead of trying to predict the age and then cutting. And it turns out that it does work pretty well, at least on the simulation. I don't know if you are familiar with these kind of plots, but let's say this is a purity completeness plot. So if you want to be pure and complete, you want to be in this corner over here, top right. I'm focusing on the right panel here and blue line only, because I'm running out of time. But basically, if you run these on the simulation, you get that you can distinguish between long-lived and short-lived with roughly 80% purity and completeness, just based on these channel images of the clump. So it's using both colors, because you have the multi-wavelength information, and it's using the shape of the clumps, which with the contrast, which helps also in determining, at least in the simulation, if it's long-lived or short-lived. So based on this success, we say, okay, let's go and try to go to the observations and see if we can, classify clumps into long-lived and short-lived clumps and see how they populate, how they distribute in candles. And so first thing we look at, I'm sorry if I'm going a bit quick, but running out of time. But the idea here is we look at the clump stellar mass functions again, but now dividing into long-lived and short-lived based on the classification. So dashed line here is candles, and solid line is Villa, candelized, okay? And main trend you see here is that there is a difference in the mass, although we didn't provide any mass estimate on the clumps when doing the classification. And you see that, so long-lived clumps, as you would expect, are more massive, and short-lived clumps dominate the population. There are way more short-lived clumps, but they are at lower masses. Other things that we look at, and then we can, this is about to be submitted, so it's still a work in progress. But the other things is that we looked at what is the distribution of long-lived and short-lived clumps as a function of the distance to the galaxy center. And again, you see some interesting trends. You see that short-lived clumps here in blue tend to be in the outskirts of the galaxy, and long-lived clumps tend to be close to the center. Again, this goes into this direction of migration, right? So these guys which have survived tend to be closer to the galaxy centers, while the ones which are short-lived are more in the outskirts. So again, points out both, the constraints on the origin more point to an in situ formation, and then we see here these trends which kind of agree with theory. I think I will skip that one. But anyway, well, the other interesting thing is we see that, long-lived clumps tend to be in more massive galaxies. And this is something that, theory predicts, but we don't know exactly what's the reason for that. But we have that long-lived clumps are more abundant in massive galaxies and even dominate over here, very massive galaxies, while short-lived clumps, tend to be in low mass galaxies. So this is again work in progress, but again is a way of showing that we can push the limits of what we have in the data and trying to get some constraints on the ages of these blobs. So I think I will stop here. I'm sorry if I went too long, but so I think one of the main results of these, this is just two simple papers that we try to address this problem of clumps. One of the main results, I think, is, when we try to study the resolved structure of distant galaxies with what we have today, which is HST data, is really pushing the limit of what we can do. And I think really the web will be very important here. I think I've shown that by using ML at different stages and combining, I think the interesting thing is to combine observed simulations, let's say, with observation. First, it's important to compare apples to apples. So when you compare two simulations, it's very important to include, especially when you go these are the limit the observational effects. And when you do these, you are able to recover some information. I think we have put some statistical constraints on the origin of clumps, which is compatible with in situ origin, given the stellar mass functions. And we alleviate the tension with lensing by showing that, in fact, the masses could be compatible once we correct from observational biases. And we also find some kind of evidences that we have in the simulation, in the observation, sorry, both short and long-lived clumps. And this opens the possibility of using these as a test for feedback models. And I think I will stop here. And thank you very much.
Thanks, Marc. This was wonderful. So we have time for a few questions. Are there any questions for Marc?
Marc, a small clarification regarding the long-lived and short-lived clumps that you defined in the candleized Vela simulation. Mm-hmm. How did you define long versus short-lived?
So this is based on Neil Mandelker's work. So basically, it defines based on how long the clamp has been, when you detect the clamp, when you have the clamp in a given snapshot, how long has been there, and also looks at the future and say how long, for how many snapshots it stays, and it puts a limit there. I don't remember exactly the time, but it's based on the past history and future history of the clamp.
Regarding that point, so whatever you just said, so just adding on to that, so you mentioned at the beginning of this talk that XC2 clumps are plausibly because of aggravated minor merging happening at high redshifts.
Right.
So for these long-lived clumps, has any one of your collaborators or you looked at their histories on the long-lived clumps?
You mean in the simulation?
Yeah, in the simulation.
No, in the simulation, they are in situ. So we classify, so we first select ex situ versus in situ. Right. And within the in situ population, we separate long and short. So all the things we use here are in situ.
In situ, okay.
Right. So, yeah. So this is again taking into account, I mean, assuming or making the assumption that the clumps we detect are in situ, which goes into the direction of what we measure with the mass function.
Okay, thank you.
So Marc, my burning question is, are the clump SEDs available?
Yes, and this is something that we can, I would be super happy to work with you guys. So they are very noisy, they are amazing points. It's a challenging problem, but I will be very interested to see if, by running more complex star formation histories or something like that, you guys are able to get better estimates to see if this overestimation is, can be, solved or at least partially solved with a better or more realistic modeling.
Right.
Yeah, I think we specialize in noise.
Yeah. So yeah, so if someone is interested in this, I'm happy to share those.
Sounds great. Could you go back to the plot where you showed like the candleized Vela versus the actual Vela mass functions for the clumps?
Yeah. You mean that one or the one?
No,
corrected?
The one with the correction.
Yeah.
So here, did you remove the XC2 clumps when you were candleizing?
So no, the XC2 clumps are in the simulation. They are those here.
Right, but in the red curve, like they don't seem to appear at all.
Yes, so you're right. So in the red curve, it depends on the modeling on the correction you use. They are very few here. So sometimes you get an underestimate over here. So they are I mean, that's why here you get this huge dispersion over here.
Right. Okay.
Yeah, but a good point.
No, I was just wondering whether in the correction that you do, like since it's making everything less massive, and since the numbers of these XC2 clumps are already small to begin with, does the correction procedure using the ANN cause these to drop out?
Right. So this is something that we discussed in the paper a lot, and that's why these two corrections are shown here. So this is one problem that we have. Maybe I can show you some. This is something that we worried a lot. This is the paper, by the way, if you want to have a look at it. But yeah, so one point exactly, if you don't apply any, so if you just correct with what you have in the CNN and in Vila, because what you want to minimize is at the end the mean square error somehow, or the of your correction, the network what will tend to do is underestimate and overestimate in the edges, because it goes to the median value. And since in Vila you don't have very massive clumps over here, very few, and you don't have very low mass, then you get biased over here. And this is the effect you just you're mentioning, is that the very massive clumps will put at low masses. And this is because implicitly is like you are doing a Bayesian estimates, and the prior you are using is the distribution of Vila. This is your prior. So if the network doesn't know, it says, okay, let's go to lower mass because it's more likely that it will be the case because this is my prior, which it biases then your estimates. Now, to correct for that, we used, a trick and correct. That's why I talked about probabilistic neural network, and try to, correct for this prior bias and use instead of the Vila prior, a flat prior. Okay, and we use a flat prior. I skip the details. You manage to, reduce. You see, compared here in the edges, you manage to reduce this bias over here and here. Okay? And what this happens is that it boosts, it allows the model to go beyond the training set and try to boost for massive clumps. And that's why, I said you cannot put really constraints on how many clumps you are here. You are sure that most of the objects that we detect are indeed low mass, but what the actual numbers of very massive clumps are a bit poorly constrained because you are limited by the training set. And this is what we try to bracket here in this plot here is the different corrections. And you see that if you use the different priors, here it doesn't change much in this regime. However, here it makes a lot of difference. You see, and this is exactly what we try to capture here, saying that because we are using this is a limitation of these, because we are correcting with some simulation, we are imposing a prior. So what happens here is very poorly constrained, but by using these two different priors, we try to bracket the possibilities, right? This is the best we could do.
I see. Thank you. Are there any other questions?
Yeah, I've got one that I typed into the chat.
Okay.
So I can't see the chat, sorry.
That's okay, I'll say it too. A lot of this analysis was about the stellar mass functions, and you showed challenges with doing that. But what about the star formation rate distribution function, which we sort of measure immediately, and presumably that suffers less from projection and contamination?
Why you say it suffers less from contamination? I would say
Clumps are selected for having very high star formation rate density, not for having high stellar mass density.
Right. That's a good point. To be honest, the constraints we saw mostly, most of the constraints about the in situ ex situ origin, especially are in the models, are in the mass. So that's why we went for the mass. The star formation rate, I haven't looked at it, how well we recover it from the SED fitting. My feeling is that it's not very good either. But maybe we could use indeed only the UV flux, right? And by using the UV flux, you get some measure, but it's also difficult to compare directly with models. So we thought, to be honest, that mass would be the less biased proxy that can be in a physical way compared with models. But maybe, I'm wrong.
Yeah, it'd be great to just investigate and find out.
Right. Good point.
Any other questions? All right. I had one final question in that case.
Yeah,
so when you start out with the Vila simulations, and like before we get into the analysis part of things where you try to recover the clumps and compare them, do in general, do the number of clumps in the Vila galaxies look comparable to what you see in the CANDELS data?
You mean before applying any correction?
Yeah, yeah. I mean,
Yes.
like, I'm not talking about masses or anything, but just do the galaxies look like what you see in candles?
Yes. So this, yeah, the Vela galaxy, I mean, it's a very small sample, but when you candleize them, they look like clumpy and I don't. They are similar. They are similar in terms of size. We know, and the sizes are similar and other stuff. I mean, it's not perfect, but they are similar. Yes. I don't know if this answers your question, but yeah. So morphologically, when you look at them, it's not shocking. You don't see, obviously, these are simulated galaxies.
Right. I mean, I was just trying to understand, like, if there is an effective prior because of the simulations themselves, like because of the feedback and other physics that you put in into the simulations, how much would that affect the results?
Well, in the correction, again, we try to correct, there's some effect of a prior, as I told you, at least in the stellar masses. But one thing that makes me confident that it's not, I mean, that there's no particular bias is the fact that here there's not any correction of it. I'm not using the simulation for anything
Right.
correct. It's just, a posteriori comparison. And already you see that, the difference between candles and Vela is, it exists,
Yeah,
but
exactly.
it's not huge. And when you apply the correction, basically the same relation stays, right? So you change the shape, but the relative behavior between the red and the blue is pretty similar. So this, that's why we push for the correction, right? If these would have been completely different, then I agree that it's a bit more tricky, because then how do you correct and so on. But so this is one of the phased evidence. And then when you apply the correction over here, this is internal to the simulation, right? So you are really correcting only for observational effects.
Right. Okay. Sounds good. Thank you so much. This was
thank you, guys. And yep. Okay.
And so in the small amount of time that we have left,